kilovolt ampere is abbreviated KVA, is a measure of apparent power. Apparent power is the product of voltage and current. It's important to understand that KVA is not directly related to the internal heating of a motor or transformer. Internal heating within these devices is determined by the power that's dissipated as heat. This heat is primarily generated by two types of losses. Firstly, copper loss, also known as I2R loss, which is caused by the flow of current through the windings of the motor or transformer, and secondly, iron loss. Iron loss is due to hysteresis and eddy current loss, and it's caused by the alternating magnetic field in the core of the device. Let's delve a bit deeper into the differences between copper loss and iron loss. Copper loss is proportional to the square of the current, denoted as I squared. This means that as the current increases, the copper loss increases exponentially. Iron loss, on the other hand, is proportional to the square of the voltage, denoted as V squared. Therefore, as the voltage increases, the iron loss also increases exponentially. It's crucial to recognize that the KVA rating of a motor or transformer doesn't directly indicate the amount of internal heating. However, it can provide an indirect indication of the potential for heating. Generally, a higher KVA rating suggests a larger winding size. This larger size can lead to lower copper loss per unit of current. However, it's also possible that a higher KVA rating indicates a larger core, which could result in higher iron loss at the same voltage. Several other factors besides the KVA rating can significantly affect internal heating. Firstly, the core design plays a crucial role. Laminated cores are used to reduce eddy current loss. These laminations help to minimize the circulating currents within the core, thereby reducing heat generation. Secondly, ventilation is essential for proper heat dissipation. Adequate ventilation allows the heat generated within the motor or transformer to be carried away, preventing it from building up and causing damage. Thirdly, the ambient temperature surrounding the device also influences internal heating. Higher ambient temperatures increase the internal heating of the motor or transformer because there is less temperature difference for heat to be dissipated. Finally, the duty cycle, which refers to the operating pattern of the motor or transformer, affects the average internal heating. Intermittent operation, where the device is not continuously running, can reduce the average internal heating compared to continuous operation. In conclusion, the KVA rating of a motor or transformer provides an indication of its apparent power capacity. While it can offer some insight into the potential for internal heating, it's not a direct measure of the actual heating. To accurately determine the internal heating, other factors such as copper loss, iron loss, core design, ventilation, ambient temperature, and duty cycle must be taken into consideration. Focusing solely on the KVA rating can be misleading, and a comprehensive assessment of all relevant factors is necessary for a reliable evaluation of the thermal performance of a motor or transformer. Consider a scenario where two transformers have the same KVA rating, let's say 100 kVA. Transformer A has a core made of high-quality steel with excellent lamination, while Transformer B has a core made of a less efficient material with poor lamination. Even though both transformers have the same KVA rating, Transformer B will likely experience higher iron losses due to the less efficient core. This means that Transformer B will generate more heat within its core compared to Transformer A. Now, let's consider the impact of ventilation. Imagine two identical motors, both rated at 5 horsepower. Motor X is installed in a well-ventilated area with plenty of airflow, while motor Y is installed in a confined space with poor ventilation. Even though both motors are identical, motor Y will likely experience higher internal heating due to the lack of proper ventilation. The heat generated by the motor will not be effectively dissipated, leading to a higher operating temperature. Furthermore, let's examine the effect of ambient temperature. Suppose you have two identical transformers, each rated at 50 kVA. Transformer 1 is installed in a cool room with an ambient temperature of 25 degrees Celsius, while Transformer 2 is installed in a hot room with an ambient temperature of 45 degrees Celsius. Even though both transformers are identical, Transformer 2 will experience higher internal heating due to the higher ambient temperature. The higher ambient temperature reduces the temperature difference between the transformer and its surroundings, making it more difficult for the heat to dissipate. Finally, let's consider the duty cycle. Imagine two identical pumps, each powered by a 10 horsepower motor. Pump alpha operates continuously for 24 hours a day, while pump beta operates intermittently for only 8 hours a day. Even though both pumps are identical, the motor driving pump alpha will experience higher average internal heating due to the continuous operation. The motor has less time to cool down, leading to a higher average operating temperature. Therefore, when evaluating the potential for internal heating in a motor or transformer, it's crucial to consider all of these factors in addition to the KVA rating. A comprehensive assessment will provide a more accurate understanding of the thermal performance and help prevent overheating and potential damage to the equipment. The KVA rating provides a starting point, but it should not be the sole basis for determining the operating limits for thermal management strategies for motors and transformers. It is also important to note that the insulation class of a motor or transformer plays a critical role in determining its safe operating temperature. Insulation materials are designed to withstand specific temperature limits, and exceeding these limits can lead to insulation degradation and premature failure. Therefore, it's essential to ensure that the operating temperature of the motor or transformer remains within the limits specified by the insulation class. Proper monitoring of temperature through sensors or thermal imaging can help identify potential overheating issues and allow for corrective actions to be taken before damage occurs. In addition to the factors already discussed, a load factor also influences the internal heating of motors and transformers. The load factor is the ratio of the average load to the rated load. A high load factor means that the motor or transformer is operating closer to its rated capacity, which can lead to increased heating. Operating a motor or transformer continuously at or near its rated capacity can accelerate insulation degradation and reduce its lifespan. Therefore, it's generally recommended to operate motors and transformers with a load factor below 100% to provide a safety margin and prolong their operational life. Furthermore, harmonic currents can contribute to increased heating in electrical equipment, including motors and transformers. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as variable frequency drives, electronic ballasts, and switching power supplies. These harmonic currents can cause additional losses in the windings and core of a motor or transformer, leading to increased heating. To mitigate the effects of harmonic currents, harmonic filters can be installed to reduce the level of harmonics in the electrical system. In summary, accurately determining the internal heating of a motor or transformer requires a holistic approach that considers various factors beyond just the KVA rating. These factors include copper loss, iron loss, core design, ventilation, ambient temperature, duty cycle, load factor, harmonic currents, and insulation class. By carefully evaluating all of these factors, engineers and technicians can ensure the safe and reliable operation of motors and transformers and prevent costly downtime and equipment failures. The location of the installation also plays a role in ventilation. Altitude affects air density. At higher altitudes, the air is less dense, which reduces the effectiveness of air cooling. Humidity is also important, as high humidity reduces the ability of air to absorb heat. Motors and transformers may have different cooling requirements based on the environmental conditions in which they are operated. Consider the application the motor or transformer is being used for. Motors used in frequent start/stop applications will have higher copper losses, while motors that run continuously will have lower copper losses. The type of load also affects motor heating. Motors driving high inertial loads require more current during startup and acceleration, leading to increased copper losses. Transformers used to supply power to nonlinear loads, such as rectifiers, will experience high harmonic currents, increasing iron losses. Be aware of the presence of any dirting factors that might apply to the equipment. Dirting factors are used to reduce the rated capacity of a motor or transformer under certain operating conditions. For example, a motor may need to be derated if it is operated at high altitudes or high ambient temperatures. The rating factors are typically specified by the manufacturer and should be carefully considered when selecting and operating motors and transformers. One more item to check is the nameplate. The nameplate of a motor or transformer provides important information about its operating characteristics, including its KVA rating, voltage rating, current rating, frequency rating, insulation class, and temperature rise. The temperature rise indicates the maximum allowable temperature increase above the ambient temperature under rated operating conditions. It's crucial to ensure that the operating temperature of the motor or transformer does not exceed the temperature rise specified on the nameplate. Finally, make sure that the equipment is properly maintained. Regular maintenance, such as cleaning the cooling fins, lubricating the bearings, and inspecting the windings, can help to prevent overheating and ensure the long-term reliability of motors and transformers. Neglecting maintenance can lead to increased heating, insulation degradation, and premature failure. So, to reiterate, the KVA rating is just one piece of the puzzle. A complete understanding of all the factors involved is essential for ensuring the safe and efficient operation of these critical components of electrical systems.